Modern physics relies on a collection of disconnected, empirically measured numbers to make our equations work. We calculate the universe with incredible precision, but our mathematical scaffolding rests on foundations we cannot yet explain. We take the speed of light, Planck's constant, the elementary charge, and the gravitational constant as given inputs. They are the fixed points of the Standard Model, but we have no theoretical origin for why they hold these specific values. General relativity successfully maps the large-scale curvature of the cosmos, yet the constants driving those curvatures remain unexplained axioms. Even Einstein's field equations require these measured inputs to function. We use our most advanced tools to measure the debris of particle collisions, refining these numbers to more decimal places. However, observing the effects of these constants is distinct from identifying their geometric source. The Space-Time Occupancy Framework, or STO, addresses this gap by re-evaluating the primitives of measurement. This framework suggests that constants are emergent properties of the physical system itself, the inevitable results of angular curvature, temporal resonance, and dimensional harmonics. To find the origin of these values, we have to look past isolated particles and toward a cohesive study of geometry, resonance, and information. To see how these properties emerge, visualize spacetime as a dynamic physical membrane with inherent characteristics like compressibility and rigidity. We can model this using a hydraulic analogy. Imagine the spacetime field as a pressurized hose through which information flows like a fluid. The membrane's allowance for angular displacement, its permittivity, maps to the diameter of this hose. A higher permittivity allows for more curvature before the medium reaches saturation. Permeability represents the membrane's angular tension, or rigidity. A stiffer wall resists bending and stores more tension within the fabric itself. The speed of light, c, represents the maximum rate at which information can propagate through this medium. It is a boundary determined by the specific compressibility and rigidity of the spacetime membrane. Mass emerges when this flow encounters a local obstruction, or kink. This kink stores angular tension across a delay, creating the physical resistance we measure as mass. This stored tension produces a buildup of thermal pressure. We measure this pressure as electric charge, the thermal expression of geometric oscillation. If the compression saturates the membrane's capacity to contain tension, the system reaches a threshold of mechanical failure. It expels the excess information as a photon of light to restore equilibrium. Within this stressed spacetime fabric, mass, charge, and light appear as the necessary expressions of geometric resistance and overflow. Tracking these interactions requires us to address a mathematical blind spot in conventional metrology, treating angles as dimensionless ratios. This convention discards the geometric relationship between linear and curvilinear frames, often requiring arbitrary patch factors like 2π to balance equations. STO introduces the angler as a dimensional operator with units of length squared per time. The angler defines an angle as a physical process, an areal sweep rate. This preserves the relational geometry that dimensionless radians discard. This dimensional approach establishes the thermal angular symmetry law, or TASK. It provides a direct link between thermodynamic temperature and the focal magnitude of angular curvature. This harmonic mapping, called the water ladder, shows how specific temperatures derive from angular compression. The equation is a reciprocal capacity relation. Temperature equals the compression constant divided by the angle. At 93,394 arcminutes, we hit the informational mass gap threshold at 66.63 Kelvin. Increasing the compression to 22,454 arcminutes aligns precisely with 277.13 Kelvin, the temperature where liquid water reaches its maximum density. The top of the ladder marks the critical symmetry window at 359.4 degrees. This corresponds to a temperature of 17,314 Kelvin, the square root of the speed of light magnitude. At this square root of C threshold, spatial wavelength and temporal frequency achieve a coherent identity. Any compression beyond this point forces informational saturation, triggering either light emission or the formation of a black hole. Temperature is the thermodynamic shadow cast by angular focal magnitude and areal recurrence. The validity of this geometric framework rests on the principle of energy unification. If the model is accurate, different physical domains must reconcile to a single coherent energy value within the Earth's reference frame. We can test this by calculating the energy across 5 distinct domains: rotational dynamics, mechanics, thermodynamics, molecular kinetics, and informational entropy. While these equations represent different conceptual fields, inputting standard values for the Earth frame reveals a hidden symmetry. Using the solar day and cycles per hour for rotational energy, we arrive at a temporal occupancy value of 383.99 joules. Mapping mechanical energy through gravitational force and the temporal wavelength of 39.11 inches yields approximately 383.5 joules. The thermodynamic, kinetic, and informational equations, using standard atmospheric pressure and the mass gap temperature, likewise converge on this value. 5 independent pathways, from rotational mechanics to bit entropy, converge on a single energy state of approximately 384 joules. We define this unit as the Kirvonic energy constant, representing the natural energy of one coherent cycle within this frame. This alignment indicates that the Earth's reference frame possesses a singular, conserved energetic harmonic that drives our local physical laws. This unified energy state allows us to derive macroscopic constants directly from the geometry of our reference frame. We can derive Avogadro's constant, Na, without relying on empirical counting. By applying Landauer's principle, we divide the total rotational energy of the system by the informational cost of one bit at the mass gap temperature. This division of energy by informational cost resolves precisely to the accepted molecular count of 6.022 times 10 to the 23rd. With the total energy and the molecular count established, the classical gas laws dictate a fixed relationship between pressure and volume. Rearranging the thermodynamic equation to solve for volume at 1 standard atmosphere of pressure, we find that the energy state requires exactly 3.785 liters. 3.785 liters is precisely 1 US gallon. Foundational units like the gallon are not arbitrary human conventions. They are emergent properties of the physical and informational architecture of the Earth reference frame. The predictive power of this framework applies to fluid dynamics, specifically the Navier-Stokes equations. These describe how energy cascades into infinitely small eddies, creating a theoretical blow-up where kinetic flux classically diverges toward infinity. The temporal containment theorem addresses this by identifying a physical regularizer for these cascades. When spatial energy cascades outpace the system's ability to smooth them locally, the energy doesn't diverge. Instead, the surplus breaks into discrete, quantized units. This excess kinetic flux is absorbed as curvature work by the Tassel operator. Every bit erasure carries a specific energetic price. Shunting this overflow into the temporal ledger provides a finite energy sink. This ensures global smoothness, preventing the energy norm from reaching an unbounded blowup. Light speed represents the maximum recursion rate of this time-encoded information. It is the boundary where space-time's capacity to contain resonance is saturated. The universe functions as a unified, harmonic geometric lattice, a cosmos where the smoothing of spatial curvature is the writing of temporal information.